Amit Srikumar is working as a pipeline engineer at DreamWorks dedicated unit, Bengaluru. He is a triple IT Bangalore alumnus. His interest lies in every technology that would help him build systems that scale. And at DDU, he is a Python developer with most of his efforts going into backend development. And he is also exploring ways to monitor applications with the ELK stack, which is Elastic Log Structure Kibana. So, welcome, Avneet, and stage to you. Thank you.
Good morning, guys. I hope you all are caffeinated enough to be awake. And since this is the first talk in this room, I would like to welcome you all to PyCon 2016. And let me take a moment to congratulate all the volunteers for their amazing job. So I think they all deserve a round. All right, so I'm here to talk about this topic, goodbye call stack, hello EDAs. Why this topic, you guys will know by the end of this talk. Before that, the volunteer did introduce me. I have a slide, so I'll just talk about myself a little. So my name is Anuth. I'm a graduate, a degree holder from IIIT Bangalore. Right now I'm working as pipeline engineer in DreamWorks Animation. And well, the customary stuff, I'm there on Twitter. That's my handle, and do look up for it. But then, yeah, let me give you a fair warning that I'm not very active socially. I think Twitter is a great platform where I can vent about products. You know, like a couple of days ago, I had a problem with some service, and I go on Twitter, tweet, and then all of a sudden I get all the attention in the world. So it's a great place to vent. But if you want to talk to me, ask questions, or have suggestions on the talk, or in general you want to know what we do at DreamWorks with Python, or you just want to abuse me for ruining your Saturday morning, then you can look me up on LinkedIn. That's Anvit Shivkumara. Okay, so first things first. Who is this talk for? So this is an introduction to this new design pattern called event-driven architecture. It is mainly focused for college-going students who are either in their third year or fourth year, or could also be a fresh graduate who just started working 1 or 2 months back. If you are a person who has already built some sort of event-driven systems and it's running and you're looking for ways to optimize it, then I'm really sorry this is not a talk for you. But I'll be more than happy to talk to you outside, interact with you guys, and see what you guys are doing or what we think should be the best way to do it. Uh, well, I really don't know why I put the third point. That this is a Python conference. But yes, in case you are very new to Python, then do not worry about this, because you'll still be able to grasp 80% of the talk. And most of the things that I'll talk about here is more towards design pattern. It'll hold good to any language that you use. So what is a call stack? So call stack is something, it's a fundamental thing in computer science. So basically, it has three characteristics. One is coordination, continuation, and context. So when I say coordination, a method invokes another method, and it waits till the invoked method to return its result to continue its execution. And continuation is, again, so you have this continuity in it. The method invokes other method, and then the method returns, and immediately the next line of the method that is calling it is executed. And the third one is context. So as soon as a called method returns, the context of the callee gets restored and the execution continues. So this is a very simple. Huh. Can you guys see this clearly? Okay. Yeah. Can we have those lights off? Okay, till the lights go off, let me just tell you what it is. So it's a very simple Python program that has two methods. One is just prints to the console, and the other one adds two numbers and returns it. So how it works is, let's say you run the command python example.py, and the call stack first gets the address of the first instruction, that is where the assignment happens, variable num1, and then it goes on, and then finally it sees that there's a call to the method write std out. So it gets pushed onto the stack, and then it does its job. And if you notice here, then the part that was calling this write std out is halted, and then the new method starts its execution. The print happens on the console, and then that returns. And the immediate line that gets executed next, so that is calling the add function. And it doesn't actually print anything, so but it does some addition operation, and that returns. And finally, again, the std out is called. That's where the result prints. This returns, and finally, the whole program ends. So this is a very straightforward. Is it better now? Okay, if you can at least make out like a rough idea, because most of you know Python, I think it should be good enough. Yeah, so this is a fairly simple and straightforward, yet a very strong concept that computer science has been employing for a very long time. Now let's look at a little more complicated example. How many of you are planning to buy the new iPhone 7? Any iPhone fans? No? Oh my, shit. Okay, so let's assume whichever your favorite phone is, it's coming out pretty soon, and you go to your favorite e-commerce website, and then you want to order the phone. So what you expect is you order the phone and you fill in your details, and the next thing you're expecting is to get the shipping ID so that you can track where it is day in and day out. And so if you employ the same call stack here, what happens is first you use the order entry service. This is basically the form that comes out, and you fill all your details in. The next step the system is going to do is check the warehouse, saying that does it actually have a phone that can be shipped to you? If that is there, then the next step would be obviously to process the payment. Nobody would want to be cheated. And then finally, the shipping services is invoked, saying that, hey, you know what, this guy needs this phone, so I think you should start shipping it. And then it comes back all the way to the order entry service, where you're actually waiting for your shipping ID so that you can track it. So again, this was still a very simple and straightforward concept, but then we all know revision doesn't hurt anyone, so let's see what we learned so far. So one thing happens at a time, like you saw, the call stack, whatever is there on the top of the stack, only that thing gets executed, and like rest all are just halted. And here we know the order of execution. We know what has to happen where. We also know who gives us the required functionality. Say, I knew that the add function needs to be called in order to add stuff. And this all happens in a shared memory. So you can only have one machine. So let's say tomorrow you have 1 million users, and your machine, you can only scale it to some extent. Beyond that, it'll be impossible for a single machine to handle such sort of architectures. But yeah, maybe it's still doable, because touching the scales of Flipkarts and Amazons, it's a dream for everyone. So you might want to be okay with it, but then when we look things, sorry. Yeah, so when we try to align the previous order your phone example more towards a real-time scenario, this is what happens. First, you enter your order, and then immediately the system needs to check where, if your address is given is right, or your phone number that you had previously registered with, that is still valid. If all those successes, then it has to check the warehouse. Now your warehouse might have a logic that if the inventory is less, then you'll have to probably send a mail to some guy saying that, hey, you know what, you need to refill the inventory. And that might lead to some other functions that, the list basically goes on. Even for process payment, it has to check what offers are there, if there is a loyalty program, or they might have a logic saying that, you know, if the order crosses this amount, make sure you give them some loyalty program. So the logic it grows to infinity. And if you look at the same call stack that we had a while ago, I'll be just sitting there waiting for my order to get completed so that I can move on with my life. So what would be the key features of a system that would basically solve that? The first one is broadcast information or events. So the same example, I order something. So there are two things that might happen. One is I'll obviously want to do some analytics. So I'll say, you know what, store this event in my data warehouse. Also, I need to process the order. So instead of doing it in 2 consecutive steps, there can just be one event that says, you know what, someone just ordered the phone. And then there's the data warehouse service that keeps listening to those events, and then there's this order processing service that keeps listening to it. And they both just grab it and then work in concurrent. Timeliness. So another important thing is no system should hold the event there. It should, as soon as the event occurs, it should have the ability to publish it. Asynchrony, this you guys might have heard a lot. So you need not wait for the other system to complete so that you can proceed with this. So this helps a lot if you have multiple users and then it just says user one ordered this and then the order processing goes back to user two and keeps doing stuff. Extreme loose coupling. So coupling basically defines what is the dependency between two systems that are connected. And so in a call stack, the coupling is very high. So you need to restore content, you need to tell what to do, you need to know where to go, things like that. So I would be lying if I say you can have like completely two disjoint systems, because that's a very ideal solution and next to impossible. But there are a few ways where you can reduce coupling. And one of those ways is introducing a new mediator between two services that talk to each other. So one service generates an event and then puts it to the mediator. And then it's the job of the mediator to make sure where this message is going to reach. And then finally, shifting responsibility to consumers. When I say consumers, I'm not talking about you and me. I'm talking about the event subscribers who would listen to an event and then do something about it. So typically what happens is you have a master database and there's one service that queries all the data. So when someone else needs the data, they query that system, get data from the database. But ideally, that's not very good. So you should never have a system, not never, it's not desirable to have a system that queries other system for data. Here what happens is each system will have all its required data. Say for example, you have a shipping service, and then there is something called consumer management. So shipping service should hold all the addresses of the user. And then if the consumer wants to update it, it should listen to an event like update consumer address, and then it'll update its own local report. So this way, it might seem initially that you're doing a lot of redundancy in data, but then on the long run, this lets you scale more. So this brings to the, how do we formally define an event-driven architecture? So event-driven architecture is a collection of decoupled single processing microservices that asynchronously emits or consumes event. So here are some terminologies that I want you guys to be introduced to, and the first one is event structure, and then there are various event flow layers that EDAs have, and then finally I'll give you some examples of how an event might flow through a system. Event structure. So event structure is just like if you're familiar with how HTTP messages go through your network, it's something very similar to that. So event typically has a header and a body. So a header will have all the metadata that is needed by the, that it should contain, like you need to identify the event uniquely. You need to have an event type. And then, of course, timestamp is very important. And then event body actually describes what happened. So event body has stuff like, this is the guy who's trying to do this, or this is the guy that invoked this thing. So example here is like, I've been taking that low inventory example for a while now, so I'm just gonna stick to that, and could be like low inventory threshold event. And other thing is, so the event generator, the person who generates event will not know who all will be consuming it. So it becomes very necessary for the generator to make the event body as descriptive as possible. So here, can you guys see this? So down below, I've just given how I feel an event structure. At least I've been working with this event-driven architecture for a while now, and this is how I feel the event body should be. And so it has all stuff like ID. I use the Python UUID package to generate IDs for the events, and you have the event type where basically it says inventory low event. So the other thing is a naming convention. So make sure that the event type, just like how you name methods, right? Make sure the event type help you recognize what it is. So event flow layers. So there are multiple layers for this. The first thing is the event generator. Now event generator could be anything. It could be a service that you're doing, or it could be just a simple method, or it could be data from your sensors like temperature or whatever it is. And I think some representative from PyCon is trying to call. Okay, anyway, I don't see anyone here. And so now you guys see that the generator could be anything. So this means that the event generator might not have a standard format. Say, for example, you have a temperature sensor. It just keeps emitting a decimal value every 5 seconds. Or you have some service and things like that that has its own standard format. So it becomes necessary for the generator to standardize this, how events are. And also, mostly in a distributed environment, these events flow through a network. So you need to serialize them. And there are a couple of ways of doing this. One is Apache Avro, Apache Thrift, and Protocol Buff by Google. And I believe Google still uses that. But I'm quite familiar with Avro, so I'll just give you a description of how it is. So Apache Avro is an open source project. It is a data serialized system. The advantage of Avro over other things is it converts to both binary and JSON. And the other thing is it is compressible. You can use snappy compression engine, and I think there's support for other stuff. And so here the schemas are in JSON, so that makes it be implemented across all languages that have JSON support. And then the other important thing is the data and the schema are always held together. So if you get an event, so a schema does come along with it, so you can actually validate the schema. So for using Avro, the workflow is generally like this. You have an event, and then you have predefined schemas for those events. So you make sure that the payload and the schema matches, and then you serialize it, and then you send it to your messaging queue. And finally, some recipient who finally reads it is gonna again validate this, deserialize it first, and then validate the schema. And if the validation succeeds, then it's gonna take some action on it, or it will just drop it. So the next one is the event stream. Now, like a minute ago, I said you have to send it to the message queue. So this forms the backbone of any distributed system. And then, so its primary job is to transmit these messages to the from generators to processing engines to any downstream activities. So there are a lot of messaging channels available. And so I just mentioned the 3 popular ones. There's RabbitMQ, there's Kafka, and then there's ZeroMQ. And fortunately, all these have Python clients, so it'll be very interesting if you guys can play around with it and see what they're capable of. So this is another crucial part, the event processing engine. So what does EPA do as soon as it gets? So it evaluates the events against certain rules. One of those rules could be making sure that the schema is according to what it expected it to, and then initiate actions that this event is supposed to cause. So those actions could be invoking a service, or saying, invoking a business process. That could be sending a mail or ordering some new stuff. And then, or it could be like directly notifying the universe. You just get a pop-up on your screen saying that, hey, something's wrong. And there are 2 types of EPAs primarily, simple EPA, complex EPA. What are these? I'll take up a few examples in the future and then let you guys know. No? Not able to see? Okay, so this is, I wouldn't say this is an example of the best event processor engine you can come up with. I would say using generators and things like that is more efficient way. But then since this talk was aimed for beginners, I've kept it as simple as possible. On top, you see an event class. And then if you come down to the end of it, basically, so what it does is it registers an event saying that, if this event comes, then there will be a callback associated with it. Make sure you call them. And then there's a register class that actually holds all the events. So it says that, event name and a callback function. So you have a service called Heartbeat that basically is supposed to receive those events and print something on the screen. So you create an instance of Heartbeat and then register saying that the Heartbeat event, whenever Heartbeat event comes, make sure you call the Heartbeat arrived function there. And then, so this could be anyone, any process running says, generate an event called heartbeat event, and then the body of that has one. So immediately it registers that, and the callback is called. So basically, this flow says how do you register for an event, how does an EPA register for an event, and when it gets an event, how does it process it? And here the processing is just printing on the console. It could be, the complexity could vary from to any degree based on your needs. So these were the some of the examples I wanted to give you guys on how the event flows through your system. And this is where I'll also talk about what simple EPAs and complex EPAs are. So let's assume you guys have a book selling service, and then one of the guys orders a book, and the first thing you do is you initiate a inventory commit event, and then next step is you go to your so the EPA that reads that, so it invokes a service that basically says, this book is already registered, and that would in turn check if the inventory is below some threshold value. If it is so, then you see that event saying that event queue. So the event generator now becomes the service that is checking for whether there's a low inventory or not, and then it in turn is emitting. So if you guys can also observe that an event generator can also be an event consumer, and vice versa. So now the event processing agent receives that, and then it could take two actions as per the definition. Like in the previous example, you saw the action was to print. So here what it does is, it publishes to the data warehouse saying that at this point in time there was a low in inventory and something was done to handle it. Also then you invoke another business process that is basically to reorder your inventory. So this is one of the simplest forms your event might flow through. So this is a little more complicated example. Let's say now we have moved on from book selling to electronics store, and we have a better funding this time. So you go a little bit fancy and say, I'm going to track my inventory through RFIDs. So the top one is basically the RFID sensor. So every time, excuse me, every time you move something out of the warehouse, the RFID emits it. And then you have this local event filter. So basically that's the business logic of it. So there you have something like, if the event value is more than $5,000, then I am interested in it, or else I'm not interested in it. So the event filter that is there, it only lets those events that are valued beyond 5,000 to go to the event channel. And then ultimately the same thing, the event process agent catches it and then it takes some action. The other one is the order entry. So this time, like you're ordering it, and then it emits event, and again you have a filter here. So the reason why you have a separate filter from your actual event generator is that business rules change every day. Let's say in the above example where you were determining high value orders to be 5,000, tomorrow you say change it to 6,000. So defining business rules in a separate event filter is always advantageous than having it embedded in your service itself. And then it's the same story. Once the EPA gets the event, it decides what to do and takes necessary actions for it. So these two were examples of simple EPAs. The next example I'm talking about is a sort of a hybrid of complex and simple EPA. So now let me define simple EPA and complex EPA. A simple EPA is one where it just receives an event and it calls the necessary action. A complex EPA is one where it receives an event and then it keeps track of the previous events and the events it is anticipating that it might get, and then takes necessary action. So this is an example of B2B. So there are two event generators again. The first one is the B2B order gateway that keeps sending you heartbeat every once in a while. And the whole point of having heartbeat is to let the consumers know that, hey, I'm alive, I'm still there, you keep listening to me. And if the heartbeat doesn't come at some point after some time interval, then there is someone who knows that the service is down, and before we lose the customers, we better do something about it. And the other event generation is the point of sale machine that you have. So So the first thing is, now the order gateway sends a heartbeat. And you have a simple event listener that keeps a response. So as soon as it gets, it takes some action. But then you have a complex event EPA that basically keeps track of it. Let's say I received this event at 9:50 a.m. today. And at 9:55 a.m., it is like, I still haven't received an updated event. So maybe I should like invoke a business process that informs the IT guy that something is down. So this is where the complex EPA comes in. And then the IT guy gets a mail saying that, the service is down, you should do something about it. And he starts it. So starting the process is again through a simple event. So the IT guy says, start the service, restart the service. So this time it's the simple EPA that gets it. You don't really need to know when the previous event came or when the other event is gonna come. So the simple EPA is initiating a process that starts the EPA. So those are some of the three examples of how event might flow through your system. Now, I know most of you attended the keynote right before this, and I think it was like the talk was pretty interesting on what are some of the policies that a distributed programmer might assume. But these are some of the things that I, as a developer working on these distributed systems and using events, everything come across. So one of the major issues that we face is you have a database, and then a person who has access to say the shell of the database just goes and updates it. And then that doesn't really cause the ripple effect of events. Let's say you update the address of a consumer, and that is supposed to cause a ripple effect across the system to update it everywhere. But if you're not generating an event to update it and you're just updating the Mongo directly, that's quite an issue because you have data inconsistency, and that might lead to a lot of corruption in data. The other one is synchronization issue. So one of the biggest problem that you're gonna face as using this architecture is systems always go down. Now you saw it could be network latency, your network is down, or there was a new computer that you didn't know of that died. So there's something called event sourcing, and if you guys have heard about Martin Fowler, he is the one who coined this term, and you should definitely look up the article. So basically what event sourcing is, you store all the events, and then let's say some events are not acknowledged, you bring back the system. You just like rerun all the events to make sure that the consistency is there among all states. And then this is little embarrassing, but it happens to me a lot. So I write a new EPA, and I say, you know what, listen to these events coming on these channels. And then I always see that I never get those events because there was a typo that was made. So you have to be very careful because there are a lot happening at one point in time. So it is you need to be very careful in naming it. That's why I was stressing on how would you want to name your event type and things like that. So again, because this system being spread over large areas and large cluster of machines, so you need to make sure that everything is configurable. So today I'm using RabbitMQ as my backbone. Tomorrow I want to change it to Kafka. So instead of going everywhere and hard coding stuff, I could just have a configuration file where I just add a new identifier saying that will have all the details of the Kafka channel that I'll be implementing. Also, logging is very important. I'm sure a lot of you guys might have heard how important logging is or how important analysis and stuff is. So events flow through a lot of systems. So if you don't have efficient logging system, you will never know what the current state of event is. So this gives you a holistic picture of, you know what, these happened, but then these points where it failed. So maybe I need to go check at that point. So logging and visualizing logging would always be of great help. So let's go back to that e-commerce thing that I was talking about. So now you have like individual services running at different places. So you have the order service, warehouse service, shopping service, and payment processing service. And then there is one event stream. So whatever order taking service does, it just generates an event and then it pushes it onto the stream, and then it carries on with its work. And then similarly, everything comes. So these are some of the things that I wanted to convey here today, because as a college student, I could not, I was never, so you had all these individual pieces of knowledge that you had. You had database, you had networks, you had OS, and things like that. But then I really could not see that anyone to tell me how to connect those all. So this was my effort in doing that with EDS, because I've been working with this for over a year, and I think it's quite interesting. So since these slides will be out there to the public, so I just added some of these references. It's definitely worth reading all these stuff. And there are tons of other things, but yeah, these are some things I thought are pretty interesting and cool. Thank you. And
We still have 5 more minutes, so if anybody wants to ask something. Hello?
hey.
Yeah, so how does DreamWorks implement EDA? Like what libraries you use and what messaging queue, what
So for us, our stack, we play around with RabbitMQ and Kafka for messaging queue, but you'll be shocked. We also have Mongo as a cap collection being used as a messaging queue, some legacy systems. So EPAs are mostly, it's just event generators that keeps running in a loop. So RabbitMQ, for example, has this IO loops, right? So IO loops keep listening to what events that the message RabbitMQ gets in, and then we have various event decorators that define what the events were, and then it gets processed. The actions get initiated. So that
Apache
could be
Avro.
so that could be anything. So let's say we have a productivity tool, and you do something. Let's say you change the asset of some shot. So that basically creates an event saying that there was a change in shot. Make sure you update wherever you need it. Yes. So we use Avro. We use Avro to define. So schemas are already defined. We use Avro to serialize it and then just post it to the.
Celery and Avro?
I really haven't used Celery, so I am not the right person to compare it. But from what I see, Celery also is a task distribution service, as in, so it distributes tasks amongst others. Avro we just use for serialization of data.
Hello.
Yeah, please.
Yeah. So, like in event-driven architecture, it is necessary to have a centralized core,
Sorry, centralized?
centralized service or a centralized server that can redirect streams to various services. Like the example you have given is like order management system, like where we have different services like inventory management system, customer management system. So, do we need to have a centralized server or service that can redirect streams?
No, so the way these messaging channels are built enables that. So you have the central of the whole architecture would be the messaging queue.
Okay.
So, and every system basically connects to it. So it's more like a publish subscribe. So you publish something, and then there could be n number of subscribers based on what your requirement is. So as such, the only central thing would be the messaging queue. You do not have any process or a service that is decentralized.
And can we have a flexibility of customizing this messaging queue or like prioritizing the messages and all?
Yes. So for that, so everything. So I just gave you I just touched upon like what Kafka is, what RabbitMQ is, but yeah. So each of them are like they have a lot to offer. So you should definitely check them out.
Thank you.
Basically, we use OpenShift, that is from Red Hat. So they give us all dashboards, and in fact, RabbitMQ itself has a plugin. I am not sure what the name is, but we use OpenShift, Red Hat support for all monitoring stuff.
Hi. So
Hi.
how do you manage failovers in this case, event-driven architectures, because the other node doesn't know about it? So in case rollbacks and failovers.
So one thing is heartbeat. So we let's say you have a database service you want to connect to, and then there's constant heartbeat going on between each of them. And at some point you have set a timeout, say 10 seconds. You do not get a heartbeat from one of the database services for 10 seconds. So you try to reconnect it forcefully. If that doesn't work, then it might need some manual intervention. So
But that's what I'm saying. I have to insert something in a table and I'm not able to connect to a database. So what about my other events that are related to this particular process or this particular order even? I may have to send email and 10 things differently.
Yes.
So I have to stop those also at that point of time.
So
How do you communicate to the system that thing?
there's always something called message acknowledgement. So you send in an event, and then if the consumer doesn't acknowledge that the message was received, that is one way of knowing something went wrong. So you might want to resend messages. Or if the consumer had died, you can ask RabbitMQ to resend all the unacknowledged messages. So that's why you would need stuff like visualizing your logs. So you will exactly know where what failed. So the thing is, it's a very vast system. It's very complicated. So the first year my manager told me, I was very excited about event-driven architecture and stuff like that. And I was like, if you don't know your shit properly, you're gonna face more problem than it'll solve for you. So there are a lot of loopholes as well. So you need to make sure that you implement stuff in a best practice way so that it'll be helpful for you to monitor things. I don't know if that answered your question.
So why did you guys choose RMQ over 0MQ?
0MQ is just socket to socket connection, right? So you have one socket, it just sends to other socket. Let's say you have like multiple
you can
consumers.
have a broker in between, as like you can have another. It has features to implement a broker in between, just like RabbitMQ.
Yeah, you just said have features to implement. So RabbitMQ gives us out of the box.
But then 0MQ is very flexible in those terms, right?
Which one?
0MQ is very flexible in those terms, right?
Right, but we had a very concise requirement of what needs to be done, and RabbitMQ out of the box gave us that. So we went with it. So it was more like a business decision because we wanted things to go out in a rapid phase rather than spending time trying to tweak it. I guess that's it. Okay, thank you guys.
Thank you, Anuth. So bunch of announcement, guys. We have open space talks going on in lecture hall 3. So those are impromptu talks, and right now the talks that are going on is interactive data plotting with Bokeh and Python Express. And yeah, you can check out there. So open spaces will be going on continuously, and also the dev sprint is going on in room number 108. So